Welcome back, everyone. And now to one, let's say, it sounds a bit odd, but one of my favorite algorithms and favorite underlying techniques since I've spent a few years of my life of investigating, researching on that particular method. So you may find me go totally banana about this cache or half transform concept. So what is the basic idea of cache, which stands for clustering in arbitrary subspaces based on half transform? The core idea is that we transform each object, so each point that we have, into a so-called parameter space, where this parameter space represents all possible subspaces accommodating this particular object. So, for instance, all hyperplanes that go through this particular object we are looking at. And this parameter space, this is now something a bit more challenging or difficult to wrap the mind around, is a continuum of all these subspaces. So it is describing like all possible subspaces as a continuous function that we have. There are several continuous functions. The subspaces are represented by a considerably small number of parameters that we have. And this half transform is actually a generalization with respect to dimensionality of the half transform, which was originally designed to detect linear structures on 2D images. Since, well, 2D, but data sets may be of arbitrary dimensionality, the authors, among which also Professor Kröger is, like in 4C, they have evolved it or further developed it to be capable to capture arbitrary dimensions. And how does it work? Well, let me better explain it here on the figures. Suppose we've got this normal feature space, data space with two axes like this one here, X and Y, keeping it simple. Then we have here three objects, P1, P2, and P3. We as humans, for two-dimensional things, we can immediately say, yep, these 3 points, they lie perfectly on a line, which is here indicated with this dashed line denoted with S. However, how can we actually characterize a line? You know, maybe from high school, there is this slope and intercept, and another representation is the translation or the distance from origin to that line, orthogonal to that line, denoted with delta, and the normal vector ns, where we take here the angle which is spanned between the x-axis and this normal vector ns. So these two parameters, this angle alpha s and this delta s, this distance, these two are spanning our so-called parameter space or half space. And now you may also know what is meant with parameter space, because given a function, in this case a linear function, we take the parameters of that linear function and span with them a new space. Now we see here that we got each object P1, P2, and P3 becoming now an object function. So since we have got here angles, we've got these type of sinusoidal functions that are going through. One nice property of that angles are by definition limited. So you have like 360 degrees. You cannot go beyond that. If you go beyond that, then you have like 2 or 3 or more rotations, but this is not actually, you still have this bounding of alpha. Delta is not really bounded, but not a big deal, as we shall see later on. However, for each of these objects, we have now an object function. But what does this object function mean? What does, for instance, this red line, this red function here mean? What is the semantic? This red function represents all possible lines at all possible angles alpha and distances delta that go through that point. So all possible angles alpha, as you see here, and all possible distances delta that go through here. So this red line characterizes this one here, and another line going through P1, and another line going through P1, and another line going through P1, and another line, and you get the idea from that. And the same holds for the function, object function fp2, this green one, it also describes all possible lines at all possible angles alpha and distances delta, all, well, not for delta because delta needs to be bounded or kept somehow. So that go through this line, and all possible lines with their angle alpha and distance delta going through P3. So this is the idea or the semantic behind these object functions. Now we ask, what does it mean if we have a point in this parameter space, in this half space, where functions intersect? What is the meaning? The meaning is that all of these object functions have a one common angle alpha s, and one common distance delta s. And this means in turn that there exists one line characterized by alpha s and by delta s, which is this dashed line s that you see here. So in other terms, an intersection point or area, as we shall see later on, since your data may not always be perfectly around one line, it may be a bit jittery, but nonetheless, one point in half space corresponds to one line in data space. And you have also the other way around, so you can say that one line in half space, one line in data space that you have corresponds to one particular line, one particular point in parameter space. And this is something which is in literature, by the way, known as the half space duality. Duality means that one line in data space is one point in parameter space, and the other way around, one point in parameter space represents one line in data space. This is the duality that we have. And this is also basically what you see here, complicatedly kind of written, is what I've explained here now on these two figures. So the properties of this half transform are that the point in data space, these sinusoidal curves that you see here now in a 3D case, and that point in parameter space, this one here, considers to a common plane or hyperplane in data space. This is this duality. So points on a common hyperplane in the data space equals like a sinusoid curves intersecting in one point that we have here in parameter space, and an intersection of sinusoid curves in parameter space corresponds to a hyperplane like this green one, accommodating this corresponding points P1, P2, and P3 in data space. So there's basically duality now visualized on a three-dimensional example. So how are we actually going to detect clusters? Now we said, what is this duality? What is the relationship between data space and between parameter or half space? But how do we find these dense regions or these intersecting regions? Well, to determine all intersection points of at least m curves in parameter space, this is the one goal. So we say we want to have clusters with at least m points, or in half space then m curves that are intersecting in a d-1 dimensional cluster. So the clusters that you find here are per se d-1 dimensional, and you see, so if I've got a three-dimensional data space, feature space, then I will get a 3-1 two-dimensional cluster, yes. However, the implementation of cache has like a hierarchical approach. It can go down, 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 so you can rerun it, or it actually does the rerun if you specify, and it tries to find lower, 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 and lower dimensional clusters. But in the first step, it will always find, if D is your original data space dimensionality, it will find d-1 dimensional clusters. However, the exact solution to check all pairwise intersections is too costly. So if you want to consider all intersections like this point with this point, this point with this point, it will be in a two-dimensional data set quadratic, in a three-dimensional data set cubic, and in a d-dimensional data set with the exponent 2 to the power of d. So it's exponential. You're not going to in a 10-dimensional data set, you would look at all possible 10 randomly sampled or brute force sampled objects and look, do they actually form a 10 minus 1 dimensional hyperplane. And this is costly, so we need a heuristic for that. And grid-based search to the rescue. You know, probably grid-based search like from algorithm like, for instance, Click. However, while Click had a static grid, if you recall, in the access parallel subspace clustering, the Click algorithm imposed a fixed grid with fixed widths at all time. Here we have something like an adaptive grid approach through this bisecting search. So what it actually does, it finds cells with at least m curves, and it does it by first like cutting this space in half among the one axis, among the alpha axis, for instance. And then it asks, where do I have still at least m curves intersecting, left or right? It turns out both of them have at least m curves intersecting. Then we cut it among the second axis, delta, and ask, okay, where do we have more curves intersecting? The top or the bottom of each of these things. So we have like, in the beginning, we have like two halves, this one here and this one here. Let me check if I can draw it actually. Pen, there we go. So what we do first, and now apologies because with this mouse drawing is a bit weird with this trackball. So we are asking for the left and right part. Do we still have at least these m curves we are looking for? It turns out yes. Then we are like saying for both here and here, do we have in the top part or the second part at least m curves? And then we say, for instance, nope, we don't have here enough curves. Then we prune it here. Then we also prune it here. This is what meant with this bisecting. Then we go here again. We say like we cut it here in half, like here and here. Then we cut it like here in half, and then we cut it like here in half. And so it continues and continues and continues until we get like here this region of interest that you see here. So this one dense region. So this is meant by the grid-based approach here. It's like an adaptive grid. We do not enforce here a fixed number of cells. So determining the curves that are within a cell, this is computable within d to the power of 3, where d is the dimensionality. However, the number of cells would be O of r to the power of d. So if you say that you want to have like, this was like 1, 2, 3, 4, 5, 6. If you increase the number of bisections, you will, so having a higher resolution of the grid, because you see here we get finer and finer and finer, it will increase the costs exponentially with the dimensionality of the data. And unfortunately, this is one of the potential drawbacks of cache. You need a high value for the resolution R. So you can't simply say, okay, you know what, I've cutted it here, that's fine, this is the region that we have here. Because what does it mean if we have such a coarse region like this one that I'm drawing here? It means we are allowing this line, we are allowing this line, we are allowing this line, we are allowing this line potentially. So we are allowing more variation, more variance of how this hyperplane can actually be oriented. And this may not be what we are actually looking for. So back to this. And the complexity, yeah, so the bisecting search is the number of bisections S times the number of clusters that are found. This is not an input parameter. The determination of curves in a cell is number of samples times the dimensionality cube. So the overall runtime complexity is S times C times N times D cube. And as a comparison, algorithms for PCA, unless we are not using something like power iteration, they also have a complexity in about D cube. So they do not differ. However, this is the overall complexity. In worst case, it can deteriorate to exponential runtime. And when does this happen? If you go for all the possible parts down, down, down to the R lowest resolution, then back, and then you choose another piece, go down, 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 finer, finer, and then back again, and then to another area of your data space, of your half space, finer and back. If you do that for all possible spots that you have, then it is kind of like equivalent to going to, because you said, if you remember, left half, right half. Then you go smaller, left half, right half, right half, then again, left half, right half of that sub partition, left half, right half, left half, and you see it's like a tree. And you've got a full enumeration, which is like exponentially growing. So you have 1, you have 2, you have like 4, you have like 16, 32, and so on and so forth. So this can happen in worst case, and we also during the studies recognize if you especially noisy data, this may happen quite often. So this is one potential weakness that can occur. So this is one insight that we had from a so-called DMAS paper, which we will elaborate later on. And how does it actually perform? Well, this is a data set. We recognize here a plane, here one line, here one line, and here one line. If we apply 4C, we see, oh, it kind of fragments and it does not fully detect here this one entire plane since it has different density. Also here you see more dense and less dense areas. So whenever it comes to density irregularities, you do not have one uniform density, something like 4C may get into trouble. It detects the clusters, but not those that are the ground truth, which we are actually hoping to find. Oculus the same, but since it has no outlier assignment, you see it takes all these whole things that are outliers and says, oh, they actually belong to the cluster. So it detects the cluster somehow, but not really well. While cache, in contrast, I mean, I know, always take it with some grain of salt. These are idealized data sets. Here we see it detects this one, this one, this one, these two planes, the blue and the purple one. What is not or not fully visible here, overlaps of clusters. This is something which is dealt in a very simple primitive fashion, which is okay. It says first come, first serve. So whichever cluster gets first, the assignment will first also have. So these blue objects may as well belong to the red cluster or not, depending on the parameter settings and depending in the order of execution, or the order in which the data is listed. So far, we shall see, because this was just like a small introduction. In the next video, we shall see a bit or elaborate more on the fine aspects, fine details of the cache algorithm and the properties of half space. So stay tuned and hope to see you again in the next session, in the next video. Take care.